Hey there, everybody. In this video, we're going to talk about orthogonal trajectories. So orthogonal trajectories are curves that are orthogonal, perpendicular to other curves. And this has applications in physics and heat flow in particular. When we look at, well, let me take it down to the paper and we'll take a closer look. Okay. So first of all, let's look at this heat flow example. So suppose you have a function of x and y, and it represents the heat at any point. All right, this is the heat at point x, y. So here's a plate, right? And at any point, it may have different temperatures. I got my space heater out. It got cold already this summer. It went from so hot to so cold so quick. I don't know what's going on. Threw me for a loop. So I got my space heater out. My table's different temperatures at different points. Suppose the temperature over here is one thing. So the heat would be given by u of x, y. You get that coordinates. Over here, it's something else. And so what we would be interested in knowing is how does the heat flow, right? The heat will, you know that if you heat up something, over time, the heat becomes more uniform, right? If you light a candle under a frying pan, right, and you let it sit there, it'll be very hot where the candle is heating up the frying pan. But if you move the candle away, over time that heat is going to disperse, and it's just kind of disperse across the surface of the frying pan. And what the heat's doing is it's moving from away from the concentrated part of the heat into the colder regions. And that's what heat does. It travels towards the cold part. And so if this represents the heat at any point, we can look at where the heat is constant, all right? So if I look at u of x, y, and I set it equal to a constant, then what I'm looking at, the curves that satisfy this, the solution curves, are called isothermals. Right? So on this sheet of paper, maybe it's constant temperature along that curve. That's an isothermal. Maybe that's where its temperature, the temperature there is 15 degrees Celsius. All right, and then maybe there's a hot spot in the middle here. So as I move towards that hot spot, it starts getting a little bit warmer. So here's where it's 16 degrees Celsius. If I look at where it's 17 degrees Celsius, maybe it looks like this. And if I look at where it's 18 degrees Celsius, I get to see things like this. Moving towards the point where the heat is most concentrated in the middle here. And it looks like there's actually 2 points, right? So these lines of constant heat are called the isothermals. And as we were saying, the heat wants to flow away from the heat source out to the colder regions. Okay, so the direction of the heat flow, if I start at this point, the heat is going to flow outwards, right? Probably in different directions. It's not just going to all go one direction, right? It's going to flow out in all kinds of directions out from that heat source. Now, what I want to think about is the relationship between the flow of the heat and the isothermal. Okay, and by the way, these would be called the heat flow lines. Right, so I want to know what's the relationship between the heat flow lines and the isothermals. Well, if it's constant in this direction, right, that means that the direction where the heat is increasing or decreasing the most must be orthogonal to that. And that's something that you should have learned in multivariable calculus. So look back in your calculus textbook for multivariable calculus, and you can prove that the direction of greatest increase or greatest decrease, both of them, are orthogonal to the curve of where the function's constant. So these lines are all at right angles. Yeah, those are all right angles. Okay, and so these are called orthogonal curves, curves that meet at right angles. Okay, and what we call these in differential equations is we call these orthogonal trajectories. Okay, so orthogonal trajectory is a curve that is orthogonal, that's perpendicular to this entire family of curves. Okay. An orthogonal trajectory is a single curve that is orthogonal to each curve in the one-parameter family given by this equation. And that's what we have here. The one-parameter family gives you these isothermals, and each one of these is an orthogonal trajectory. Okay, let's go look at some examples. So here we have a one-parameter family of curves. Okay, I took a very simple one here. It's x squared plus y squared equals c. I think we know what these look like, and you can see one right over here. It's a circle, right? And c has to do with the radius, right? So as I vary c, you can see I get a different curve. These are like my isothermals. Various isothermals by varying c. What would my orthogonal trajectories be? What do you think? I need curves. I need to think of a curve that's orthogonal to every single one of these circles. Well, if you think about it, you'll realize it's a straight line, right? That straight line is orthogonal to every single one of these circles. And not only that, but there's lots of them, right? I can take any line through the origin, and it's orthogonal to every single one of those circles. So a line, y equals mx, is an orthogonal trajectory to this family. Let's look at another family. Here's another family of curves, a one-parameter family. I'm varying the constant, and we see we get a family of hyperbolas. Right? And the question is, what are the orthogonal trajectories to this look like? This one's not as obvious. Turns out they're also hyperbolas, right? So this, look at this. That is always orthogonal, right? To every single member in this family, that blue hyperbola is orthogonal to every single one of these, right? And in fact, there's an entire family of those, right? These are all orthogonal trajectories. Another family of hyperbolas, right? And they're all given by x squared minus y squared equals m. Okay? And I wrote down, I was just thinking of showing you this. This is pretty wild. Here's a family of curves. Look at this. This is from sine x times cosine y equals c. Think about what the orthogonal trajectories of these would look like. Right? I'm not going to give you the answer here, but it's interesting to think about. As I vary the constant, you can see how this family changes. Kind of interesting. It even becomes a grid at one point. I like that. Anyway, let's do this mathematically. Let's go back to the circle example and think, for this family, how would I find, using the power of differential equations, the orthogonal trajectories? We know what the answer is, right? So let's see if we can prove it. Okay, so let's go back down to the sheet and see what we're dealing with here. So the family of curves that we're looking at, u of xy equals c. Well, in this case, u of xy was x squared plus y squared equals c. So there's my u of xy. Okay, and that gives me the family of circles. Now, I want to find those orthogonal trajectories. Well, orthogonal, what does that mean? Well, I know that two lines are orthogonal when their slopes are related in a nice way, right? So if I have a line and another line, and I want them to be orthogonal. Well, let's say the slope of this line is m1 and the slope of this line is m2. Okay, how are their slopes related? You should remember from algebra that m2 has to be the negative reciprocal of m1, right? That's what it means for these to be orthogonal, okay? So if we're dealing with curves, well, how do I find the slopes of those curves? Well, the curves, the slopes are given by y prime, dy dx, right? So I have to get y prime out of this. So what I'm going to do is turn this into a differential equation, okay? And so I'll just differentiate. So let's just differentiate, implicitly differentiate through by x. So go ahead and do that on your own, and we'll check our answers together. So 3, 2, 1. When you implicitly differentiate with respect to x, you should have gotten this. Okay, so this is just implicit differentiation. Okay, and we get a differential equation. I can divide through by 2, so those don't need to be there. Let's solve for y prime. Okay. Do I really need to do that? Yeah. So let's solve for y prime. Y prime is equal to negative x over y. Okay. So what I've done is I've written the differential equation in this form, y prime equals f of xy. The form that we've become very familiar with. We like to get our differential equations to look like this. Okay. So now how do I get the orthogonal trajectories? This is describing the circles, right? This is the differential equation that describes the circles. I want now a differential equation that describes those lines, the orthogonal trajectories. Well, I'm going to use this, right? The slopes of those new curves that end up being lines in this case has to be the negative reciprocal of the slopes of the circles. So it must be the negative reciprocal of f, right? So for my orthogonal trajectories, what I'm going to do is I'm going to set up a new differential equation, y prime equals the negative reciprocal of this. And this is how you'll always do it. You're going to first write down this, find your differential equation, and then secondly, you're going to do this. And in this particular case, I'm going to find the negative reciprocal of this. This is my function. So what's the negative reciprocal? It's y over x. Okay, so I'm going to ask you to solve this on your own. We'll check our work together. Okay, so 3, 2, 1. Okay, let's see if we agree on our answers. This is a separable equation, so let's divide both sides by y. Separate the variables here, right? Anti-differentiate both sides. Let me not use C. I used C up here. Let me use a different letter. And I'm actually going to use B twiddle. We've done that in the past because we know this is going to become a new constant. I'm going to raise each side to the power e to get rid of these logs. So I get absolute value of y equals, oh boy, so, okay, I'm going to call this B twiddle twiddle because that's also going to change, all right? When I take the e to this power, it cancels the logs, and then e to the b twiddle is b twiddle twiddle, right? But we know that the absolute values here can be absorbed in the constant, right? So that's what we're going to do. We're going to get rid of the absolute values by putting, whoa, you know what we'll do? We'll call that m. Why don't we just do that? Y equals mx. Because we know that ends up being the slope of the line, so let's just call it m. And that's it, right? Those are our orthogonal trajectories, right? So where did my browser go? There it is, right? Y equals mx is exactly what gave us, where did you go? There you are, these guys, right? These are the curves that are orthogonal to the family that we started with. All right, so pretty straightforward thing, I think, right? It's just using the negative reciprocal property and orthogonal trajectories. That's all I had for this video. So catch you on the next one.